Okay, so today we're going to be talking about under what conditions can we use a T procedure. Can we create a confidence interval using the T distribution or having our critical value be T star? And the key thing here is that our confidence interval is exactly correct if our population distribution is exactly normal. Well, in real life, nothing is exactly normal. Everything's kind of approximately normal. So the usefulness of the T procedure depends on how closely or how close our distribution is to being normal, or how much it differs from a normal distribution. And so what we were talking about yesterday, or in class, or today in class, or yesterday, depending on when you're watching the video, was not that the population wasn't normal, is we started playing around with our sampling distribution, and if we used the standard deviation of the sample, which is S sub x, instead of the standard deviation of the population, how did that affect our calculated values? And we found that that created a new distribution, the T distribution. So we can use the T distribution in this scenario, but only if the original sampling distribution of x bar is approximately normal. And so how much off can that be? An inference procedure is called robust if the probability calculations involved in the procedure remain fairly accurate when a condition for using the procedure is violated. The normal condition is going to be violated. It's going to be, because no population is exactly normal. And so the question is, how badly can we violate it and still be okay? And the answer to this is that the T procedure is actually very robust. As long as there's no major outliers or strong skewness presence, we're going to be okay. And of course, larger sample sizes improve the accuracy of critical values from T distributions because the central limit theorem kicks in. So how can we tell if our population is normal? And so what we're going to do is we got to comment on it. You have to check conditions. All right, on an AP exam where you're constructing either a hypothesis test or a confidence interval, hypothesis testing is the next 2 units, you're going to have to check the conditions. The conditions are going to be random, normal, and independent. It's going to have to be done on every single problem. If you don't check conditions, you're going to lose points. So if we check the conditions, it's an easy points to pick up. It's really easy to do this. So you can't just say assume normality. You have to show it. And if we're checking for proportions, right, it's easy. It's the NP is greater than or equal to 10, or n times 1 minus p, n times 1 minus p hat is greater than or equal to 10. That's for proportion. But what we're talking about here are T distributions, so it's going to be a situation where we're estimating mu with x bar. So what do we need to do? We need to show normality. So the easiest way is if n is greater than 30, then central limit theorem kicks in and we are all good. But if not, if the sample size is less than 30, then what do we do? And generally what you're going to have to do is you're going to have to show a graph and give an appropriate comment. Now the graph you can show can be a histogram. It can be a dot plot. It can be a normal probability plot, which we will go over how to do again in class. Right? It can be one of those three, and it doesn't have to be perfect, but it has to be a rough sketch of it, and then you have to comment on the shape of the graph. You can't show the graph and you can't comment on the shape of the graph. You must do both. Except in cases of small sample sizes, the condition that the data come from a random sample of randomized experiment is more important than the condition that the population distribution is normal. And so here are some practical guidelines. These are not set in stone. These are kind of this is the real world, right? Nothing ever goes perfectly. So if sample sizes are larger than 30, game on. If sample sizes are larger than 30, then we are all set. Because if the sample size is larger than 30, then the central limit theorem kicks in, and it says it doesn't matter anything about the shape of the original population. It doesn't matter anything about the shape of the distribution of the sample, because if sample size is greater than 30, then the sampling distribution will be approximately normal. Central limit theorem is amazing and incredibly useful. Now, if we have a really small sample size, less than 15, if the data is roughly symmetric, has a single peak, and no outliers, then we're okay to use T procedure. If we see strong skew or any outliers, and remember we had a definition for outliers, 1.5 times the IQR away from either Q1 or Q3. Then if we have either one of those, then we cannot use it. If we're between 15 and 30, and this is generally where you're going to be on the AP exam, as long as there's no strong skew or outliers, it's okay. So in the example yesterday in class, we had a sample size of 18, or today in class, depending on when you're watching the video, we had a sample size of 18 rolls of toilet paper. So we were in this 15 to 30 range. So it didn't look approximately normal, but there was no strong skew and there were no outliers, so we were fine. If we're less than 15, when we squint, we need to see the normal distribution a little bit. So, and we'll play with this in class. We'll play with that in class, but those are our rules of thumb, and that's how we're going to comment on normality, the normality condition on any problem where we're asked to construct a confidence interval. Remember the rubric for the AP exam. If there's going to be 4 points on these kind of problems, and 1 point is going to be checking conditions. And if you don't address normality, generally it's going to drop that part from an E to a P, or a lot of times from an E to an I. It's all or nothing. There'll be 3 conditions, and you have to check all 3. So we started off with, we said, well, hey, in a perfect world, our margin of error would be this. But in real life, we don't know sigma. So we replace, instead of calculating off here, we'd use a t distribution with n minus 1 degrees of freedom. You can either get your t values from the chart, or if it's a specific value and you're trying to find a specific percent, you can always use the inverse t on your calculator. And we'll go over that. It's like the inverse norm on your calculator. You can do an inverse t and get the area, and we'll talk about how to do that. We'll practice that in class. So generally, instead of margin of error, we're going to be using the standard error. And standard error is t star times s sub x over the square root of n. That's standard error. Our general formula for a confidence interval for estimating mu would be x bar plus or minus t star over s of x divided by the square root of n. And t star, we're going to need to know the degrees of freedom. And degrees of freedom is going to be sample size minus 1. You have to check the conditions. We have to check whether it's random, normal, independent. This is the 10%. We can't sample more than 10%. Normality is going to change depending on what procedure we're running. And we went over the robustness of T before. So that's it, just a short little video. We're going to be doing a lot of these in class next time. That's going to be the goal. So I'll see everybody on Friday, assuming no snow.